Good morning, students. Today we are going to discuss elements of symmetry. Elements of symmetry offers a simple device to decide whether the molecule or object is chiral or not, whether it is superimposable on its mirror image or not. When a molecule has a plane of symmetry or center of symmetry or n-fold alternating axis of symmetry, it is superimposable on its mirror image and it is a chiral, that is optically inactive molecule. Elements of symmetry. Three major elements of symmetry are axis of symmetry, which is denoted by Cn. Second one is plane of symmetry, which is denoted by sigma. Third one is center of symmetry, which is denoted by Sn. Now we are discussing axis of symmetry in detail. When an imaginary line or axis can be drawn through a molecule so that rotation by 360 by n gives the molecule indistinguishable from its original, then the molecule is said to have axis of symmetry, that is Cn order of n. Just see this molecule. If we draw axis of symmetry from the center of molecule, and if we rotate this molecule, give one rotation, we got this type of structure. Just see, this chlorine comes here while this chlorine comes here after rotation. When we give again a second rotation, we see that our this structure and this structure is identical. So we simply say that this molecule possesses C2 axis of symmetry. Now we are going to discuss plane of symmetry in detail. The plane which divides a molecule into two equal halves which are related as an object and mirror image is known as plane of symmetry. Just see the example of mesotartaric acid. Here, if we draw an imaginary plane, this plane bisects mesotartaric acid into two equal halves. Just see, above portion is exactly matches with the lower one. So that's why tartaric acid contain plane of symmetry, and that's why this molecule is optically inactive. Now we are going to discuss center of symmetry in detail. A molecule is said to have center of symmetry if all straight lines that can be drawn through the center of molecule meets identical atoms at equal distance from the center. Just see this example. This is the center of a molecule. If we draw a line from here, we see that identical group is present on opposite side. If we draw a line from here, we see that identical atoms are present at opposite side. If we draw a line from here, we see that identical group, that is COOH, present here. It is the hydrogen. If we draw a line from here, we see that there is identical atom present on opposite side. That's why this molecule possesses center of symmetry, and that's why it is a chiral molecule. Now we are going to see molecular chirality. Molecules of the cave exist in an enantiomeric form, that is pair of non-superimposable mirror images, and are described as chiral. And the carbon atom with four different achiral atom or a group as a substituent is called stereogenic center or stereocenter. So first condition for a stereogenic center for a chiral molecule is the presence of stereocenter usually leads to molecular chirality. A tetrahedral atom, that is carbon, gives a stereo center provided on interchange of two groups leads to new stereoisomer. The presence of stereo center in an organic molecule is a sufficient condition for a chirality. It is important, but note that it is not a necessary condition. It is sufficient condition, it is not a necessary condition. Next point is several molecule display chirality, that is optical isomerism, in absence of stereo center, that for example chiral biphenyl. Thus compound is chiral if it is not superimposable on its mirror image. So the minimum condition or sufficient condition for chirality is presence of stereo center. What is stereo center? Stereo center simply means a carbon atom having 4 different substituents. So just see the example of biphenyl. In this example we see that there is a no chiral carbon is present. Beside that, this compound is optically active. That's why presence of stereo center is a sufficient condition, but it is not a necessary condition. Just see, if we draw a mirror here, so we got its mirror image, and that's why these biphenyls are enantiomeric. This pair is enantiomeric pair. Now just see this biphenyl. In this biphenyl there is a presence of plane of symmetry. If we draw plane of symmetry from here, the left half is exactly matches with the right half. That's why this compound is optically inactive. Now we are going to see what is meant by enantiomers and what is meant by enantiomerism. A compound with an sp3 hybridized carbon with a 4 different substituent is called chiral compound. For example, 2-butanol. Just see, this is the structure of 2-butanol. In 2-butanol, second number of carbon atom is stereo center, that is this carbon contain 4 different substituent. It is attached to 4 different substituent. That's why it is chiral, that is it is stereo center. Now just see, name of this compound is S2-butanol. If we draw mirror here, we can easily draw its mirror image, and name of this compound is R2-butanol. So this pair of butanol molecule are termed as enantiomers, that is opposite. Enantio means opposite. Enantiomers are defined as non-superimposable mirror images of each other, and isomerism existed by them is called enantiomerism. Also see the example of D-glyceraldehyde and L-glyceraldehyde. In a glyceraldehyde, this carbon is chiral in a nature. So one can draw its mirror image by putting mirror here. So because of that, this OH molecule is shifted, or it is drawn on left hand side. In this molecule, it is on right hand side. Now we are going to see properties of enantiomers. They have same physical and chemical property in a chiral environment. They rotate plane polarized light in opposite direction by same angle. For example, D-glyceraldehyde give plus 13.5 degree rotation, while L-glyceraldehyde give minus 13.5 degree rotation. So there is just change of direction. They have same melting point and same pKa values. Enantiomers react with achiral reagent like NaOH with same rate. Enzymes which are chiral react with enantiomer at different rates. Now we are going to see compound with one stereogenic center. Example is lactic acid. Lactic acid is an example of compound which show optical isomerism. It contains one stereogenic center. So this is the formula of your lactic acid. So just see, in a lactic acid, your second number of carbon is chiral carbon. So it is stereogenic center, inactive. We are now going to discuss in detail optically active form of lactic acid and optically inactive form of lactic acid. So first form is plus lactic acid. It rotates the plane of polarized light to the right side, that is clockwise direction, and that's why it is called as dextrorotatory. Negative lactic acid or minus lactic acid, it rotates the plane of polarized light to the left, that is anti-clockwise direction, and is called as levorotatory lactic acid. Now we are going to see third form of lactic acid, which are inactive in nature, which are optically inactive. It is denoted by plus minus lactic acid. It does not rotate the plane of polarized light. It is optically inactive. It is an equimolar mixture of positive and negative form of lactic acid. It is also known as racemic mixture. Now what is meant by racemic mixture? Racemic mixture is the equimolar mixture of positive and negative form. In our next class, we are going to discuss compound chiral and achiral molecule with two stereogenic centers. Thank you very much.